I am Anil Kumar. Welcome to my series on Combinatorics. We are going to discuss a very important identity which is observed in Pascal's triangle in this particular video. It is called hockey stick identity, also Christmas stocking. Many examples and test questions are based on this particular property. I will discuss at length what the property is, how can we solve related questions, and also how to prove it, right? So the idea here is to understand the pattern, which is popularly known as hockey stick identity. We'll also see a column version of it, and then solve examples and prove the identity by the method of induction. As you can see on the right hand side, I've made a diagram. Here's a Pascal's triangle. In a Pascal's triangle, every element is sum of the closest elements on top of it, right? So that's how you get the elements in the Pascal triangle. Now, here are a few important things to observe. If you look into this diagonal, which is marked in yellow, you will see as you move along the diagonal, adding these numbers like 1, 2, 3, 4. If you add these four numbers, they are in a sequence. 4 times 5 is 20, and half of that is 10. So that is the sum of these numbers. So if you move along a diagonal starting with position 1, in that case, the number following is the sum of those numbers in the diagonal, right? Now the position of this number which follows is slightly different when you're moving from the right side or from the left side, right? So look here at the other pattern which I have shown. You would also move from this place 1, 6, and 21. When you add, you get to that number. Do you see on the left side? So the sum is on the opposite side of the movement of the diagonal. That is what it is. And it gives you a look of a hockey stick, and that's how it has got its name. However, these two movements make a huge difference in the final answer of a pattern which is sometimes misinterpreted by many students. Now, here is the formula which is commonly used to find the sum of all these elements in diagonally placed hockey stick arrangement. So, if you move in the southeast pattern, right, that means going down and right. So that I'll call this one as the southeast pattern, right? So this is southeast pattern for us. So if you move in this particular direction, you see you end up on the left side, and the diagonal number actually remains. So in this particular thing, what you notice is that the diagonal number remains the same as that of the previous one, right? So R and R matches. However, the row number increases, right? So you see that the row number increases. On the other hand, if you're moving in the southwest direction, right? If you're moving in the southwest direction, that is this direction, which I'm treating as southwest, what you notice is both row number and diagonal number increase by 1, correct? So in a multiple choice question and even otherwise, this simple variation which you see makes huge difference, and many times students get wrong answers. So first thing to be noticed here is that it depends on where you start, right? So the position on the southwest starting will be kind of, you can say, NCN, right? Do you understand? And the position starting from southeast will be NC0, and choose 0, right? So that is how it makes a huge difference starting from where and in which direction you're moving. So let's try to see this pattern when we arrange our triangle in a column form. Now that is the column form which is very pretty but hardly seen in many books. And many students, they may find it very useful and interesting. So what I've done here is written the same pattern, right? So the pattern 1, 2, 3, 4 up to 7 I've just taken. And you notice that its sum is on the right side shown here, right? So you add all the elements in the column, and where is the sum? Row and column number increase by 1. Do you see that? So it is similar to your southwest pattern, correct? So similar to your southwest pattern, so we'll treat this as our southwest pattern, correct? So that is southwest pattern, and the result is that when you add numbers starting from 1, that is essential. It has to start from 1. Starting from 1, the row number and the column number both increase by 1, right? So there are a couple of examples which you can notice. Perfect. Now, before getting into the proof of all this, let's take an example itself. Now, the question for us is we need to find the sum of 1C1, 2C1, 3C1 up to NC1, right? That is what we need to find. And we know it is n plus 1, 2. So that 1 gets added to 2, right? So 1 plus 1 on both the sides. So this is the kind of pattern which I was talking about, that it starts from southwest side, correct? So that is your southwest pattern. And as you can clearly see, both row number and the column number, or in the case diagonal number, increase by 1. So based on this, we have taken an example. We'll actually prove it later, right? We'll prove it by the method of induction in just about 2 minutes. Okay, so here is a simple example. If we have to add 1C1 with 2C1, 3C1 and 4C1, what do we get? That is what we want to understand. Well, if you know the formula, you know the result also. We are expecting 5C2, right? That is what we are expecting, right? Okay. From the formula. Now let us see how can we derive at it algebraically. So here is the solution right before us. So as you can see, we're moving along this particular diagonal, which is highlighted in yellow, right? So beginning from 1C1 plus 2C1, 3C1, 4C1, as you know, 1C1 is 1, right? So we know the value of 1C1 is 1. So let me write down here, we know 1C1 is equal to 1. So that is being replaced by 2C2, right? So that is being replaced by 2C2, which is also 1. The idea here is that we can use the basic iteration rule that should help us to converge at the result, right? So that is also called a telescopic property of this iteration rule, right? So we are going to adopt this telescopic property to converge to our result, right? So we replaced 1C1 with 2C1, whose values are 1, and then we have just copied the other numbers, right? So when you combine 2C2 with 2C1, what do you get? Using this property, we get 3C2, right? So 3C2 is what we get. So combining these two, we get 3C2. Now we can combine 3C2 with the next element, right? That is how this telescopic property works, as you know. So we get 4C2 now, and then 4C2 and 4C1 when combined will give you 5C2. So as expected, we did get our result, which is 5C2. Perfect. So I hope that makes it absolutely clear that when you're moving along southwest direction, in that case, row number and the column number, you can say diagonal number, increases, right? As shown in this particular pattern in yellow. Same thing will happen if you have something along the diagonal 4 as we have shown in green. So those will be similar results, right? Now let's take up another example in which we are going to move in southeast direction, right? So here you can see I've highlighted these 1, 3, 6, 10, and 15. If you want to add these numbers, what do you get? You get the number 35, right? Which is on the left side of your diagonal, right? Which is on the left side of the diagonal. And so in this particular case, the row number increases, but the diagonal number remains exactly the same. Just notice the difference, correct? So what I'm trying to say here is that in our example, which is where the diagonal is moving southeast, you can see, right? In that case, the sum is moving left side, the opposite direction, opposite to the diagonal movement. That is what critical is. Okay, so we have to begin with 1 for sure. So we have 2, 0 as our first element, 3 1s, 4C2, 5C3, 6C4. What is the result? Well, clearly, the result should be that it should be 7. And since we still remain in the same diagonal, the end result will be 4C, 7C4, right? 7C4. In the previous case, you saw that the diagonal number increased. Not in this case. Perfect, as you can visually see also. And now, with the help of this example, we'll adopt the similar method, the same approach. The iterative formula will be utilized to converge, and then we'll have our solution, right? So to begin with, we have 2, 0, which could be written as 3C0, right? So 3C0. Once we do that, we can combine 3C0 with 3C1, and what we get is 4C1, correct? So that is the whole thing. So we combine these two to get 4C1, then we combine 4C1 and 4C2 to get 5C2, and then we combine 5C2 and 5C3 to get 6C3. Combining 6C3, 6C4, we get 7C4, and as expected, that becomes our answer. You get the idea, right? So you converge to your answer in this particular case. And remember, we are moving in this particular case southeast direction. As you can notice, these numbers, diagonal numbers, match. They don't increase. However, this number increases by 1, correct? As expected. Now you could have many test questions based on this. Here is another series for you. Can you write down the answer for this? 7C0 plus 8C1 plus 9C2 so on till 526, 519. Well, you can clearly see as you see that number 0, you know it increases from 0, 1, 2, 3. So definitely we are going in the southeast direction. So that gives you southeast direction. So this number here will be added by 1. So you get 527. However, this number here will remain same. So it will be 519, and that will become our answer. So 527C 519 is your answer for this particular case. Once you're clear about the concept, then it is not difficult. So in both the cases, what we see is that you have to move along the diagonal, and the sum lies in the next row, but opposite to the diagonal direction. Correct. Now let's take up the proof of the hockey stick identity, right? So in the first case, I'm taking the diagonal sum property. It is also called mainly and popularly as hockey stick property, right? We're taking the case where the movement is southeast. So in this southeast movement, as we discussed, what really happens is that we are southeast is this, right? So we are moving south, and then we are going towards the east direction. We're considering this type of a movement, correct? That is our southeast movement. Let me write down. Correct? That is the case. So we'll begin with the sum of these elements which are along this path moving southeast. So the sum of elements in the diagonal starting with 0 is equal to the next element down diagonal in the opposite direction. So that is kind of important, right? So the sum is we have to start from 1 is equal to the next element down diagonally in the opposite direction. So you're going in southeast direction. The sum finally will land up here in the opposite direction as shown in the highlight color of red, right? So you could write this in sigma notation in general as sigma, where I changes from 0 to r of n plus I ci is equal to n plus r plus 1 cr, right? So that is what we need to prove. We'll prove by the method of induction. So in the method of induction, what we do is first we will check the initial case. If I write r equals to 0, then we have to check whether the statement is correct or not. So substituting r equals to 0, we get sigma nc0, which is 1. And on the right side, we get n plus 1 c0, which is also 1. So that is true, right? So that is true. Now, we will say, let it be true for a particular value, correct? So, that is the method to be followed for any proof by induction. So, let it be true for r equals to k, right? Where k is greater than or equal to r. Okay, in that case, in sigma notation, the sum of elements will be n plus k ck. And what are we expecting? The result should be n plus k plus 1 ck. That is what we are expecting. Since we replaced r with k in the given expression, we have replaced r with k and we got this. And we will say, well, let this be satisfied. Okay, let this be true. So that is our let statement. We're saying let this be true. Okay. Now, if that is true, we have to only prove that if r is equals to k plus 1, the next consecutive term, even then it should be true. That's the whole idea, right? So, replacing k with k plus 1, what do we get? Well, let me write the sigma notation itself, breaking it down with the sum property of the Pascal's triangle. We can write this as sigma from I equals to 0 to k of n plus k ck plus n plus k plus 1, k plus 1. How did we get that? We know that the sum of elements from the previous two, right, add up to the next one, correct? That is the property, right? So that is how we could write from here to this. So that is this property by definition, right? So that is iterative rule. Okay, now next step. We already know from our first case that this particular expression, let me highlight in a different color, is basically equal to that. Correct? This is what we have assumed. If r equals to k is true, then we have to check k plus 1. So that is true. So we replaced and got the next statement, which is n plus k plus 1 ck is equal to plus n plus k plus 1 k plus 1. Correct? And now again, we applied the Pascal's identity, the same identity. Next row element will be what? Will be this, right? So we get our answer, which is n plus k plus 2 ck plus 1, correct? So this combination here itself gives you the next element in the Pascal's triangle. And that is how we prove the identity. And this one has been done when we move diagonally southeast. Perfect. Now let's take the next one where the movement is from southwest, is in the direction of southwest. Okay, so Hockey-stick identity or diagonal sum property will now take up the sum of elements in the diagonal line starting with 1 is equal to the next element down diagonally in the opposite direction, correct? So this definition works for both, right? So that is kind of important to understand. It's the same definition. It works for both. However, the results are slightly different. When we move from south west, our row number and the diagonal number both increase by 1. That is a huge difference, correct? Right. So we need to prove that the sum of ICR when I changes from R to N is N plus 1 CR plus 1. Perfect, where N and I are both in natural numbers greater than or equal to 0. Okay, integers greater than or equal to 0. We'll again prove by induction. So initial condition is, in this case, I equals to R, right? So we'll put R, and then what we get? Well, sigma of RR is 1, right? So in that case, we know both sides are equal to 1, and therefore it is true for the initial condition when n is equal to R, right? Since this varies from I equals to R, from R to N, right? So we are going from R to N, and that's how we move southwest. Clear? Now, let it be true for n equals to k. This is what the method of induction is. So when it is true for k, in that case, we know that the sigma of ICR when I changes from R to K should be equal to K plus 1 CR plus 1, right? Now we need to just show if I replace n with k plus 1, right? So now if I write n equals to k plus 1, then is it true or not? This is what we need to check. So we have replaced n with k plus 1 right there. And once we do that, in this particular case and expand, we get what? We get k plus 1, r plus 1 plus k plus 1 r. And now from the Pascal's identity itself, we get k plus 2 c r plus 1. Perfect. That is how we prove it. So that is so simple. So what we did once again is we have taken for I from R to K plus 1. Do you see that? So we changed it to K plus 1, and that gives us this value of K plus 1. And we already know that sigma for the value of the first one is given to us as k plus 1 r plus 1. When you add k plus 1 r from the iterative property, we get k plus 2 c r plus 1. And that is the proof of it. So I hope it's absolutely clear how we can use the hockey stick property to solve many questions. So in case the sum of elements in a Pascal's triangle is along a diagonal line starting from 1, that is kind of very important, starting from 1. In that case, the sum of all these elements is the next element along the diagonal but in the opposite direction. Do you see that? And that is how we get this hockey stick pattern, which is also called Christmas stockings. So with this proof and the examples which we discussed, I hope the concept is absolutely clear. Feel free to write your comments, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.